robotics and automation. So this series of recorded lectures relates to robotics and robotics as used in automation, so to say. This is complemented by some PDF documents together with these slideshows and these presentations. So part one, introduction of the whole topic, so to say. So about this one, I will provide a general overview with main focus on industrial robotics, some main characteristics of robotics, application examples, trends, and some outlook for research and development within the area, or given a broad perspective of it. So industrial robotics, the highlights of its use today and present technology and impact in industry, and some historical background related to that one. And we can also conclude that if you look at industrial robotics automation, there is some relation to service robotics and vice versa in these kind of developments. On the other hand, service robotics has taken another path from beginning, but they are merging together more or less from a technology point of view. So what are we looking for when we look at automation and using robots in factories? What to think about now is low-cost products, and we move towards a varying capacity for different types of products or variants of those products. And when we look at premium and high-end products, we look at high quality. And basically, we can see that if we have low-cost products with the extremely high volume, maybe robots is not the first choice. We use special dedicated machines. But on the other hand, if we increase the number of variants, and by that decreasing the total volume of that variant, that makes it difficult to produce in dedicated machines, then robots might be a good solution to that. So what is happening is that we have high volume products with variants in many cases, not all, but in many cases. We might have low volume products with frequent changeover, and we have a varying market requirements, local and global. And these aspects create some challenges for any manufacturer, I would say. And then we have work processes. And in many cases, we have to be able to produce products using processes that is not possible with humans. What can it be? Well, take anything like a laser processing. Lasers cannot be manipulated by humans. They have to be manipulated by machines, typically then robots. There are many cases where we have toxic or dangerous environments around processes. Like, spot welding is not performed by humans today, unless in very dedicated or special cases. There might be spray painting in high volume that we don't do by humans. It might be chemical substances. It could be high temperatures, whatever, really. Cleaning of castings and so on. So I will provide some examples. Some keywords relating to the use of robots, or when the requirements from the manufacturing system is in a way that we think about robots relates to flexibility. Flexibility in meaning the use of what we are going to do actually is changing over time. So it's flexible in that way, in that sense. So flexible in the use of machines, tools, processes, and the operation of that. The capacity is variable, on demand, meaning that we only produce what we can sell and deliver to the customer that is paying for that. And if there is no demand, we hold. Quality, to produce at a consistent and controllable quality. No bad object, no bad products. This consistent quality is really important. Efficiency, that we have a production workflow that really works in an efficient way. So industrial users and use. Some examples. Of course, in robotics, we talk about automotive industry, cars, trucks, and so on. And we have processes like spot welding, arc welding, gluing or dispensing, spray painting, assembly, for example. Electronics industry is, together with automotive, the biggest users of robotics, of robots, industrial robots. And that can be assembly of electronic components, packaging. Packaging comes at every branch actually, but with electronics there's so many products that have to be packaged. Food industry, pick and place, packaging, providing a clean environment, really important. So on, if just a few examples of how it can look. This is from automotives, so we have spot welding and production line moving forward and the robots are standing still, and usually there are many robots or as many as you can place at those places doing spot welding at the same time at several places. Pick and place. This is a Delta type robots picking croissant or cookies or whatever at a very fast rate. Typically, I mean, one croissant at a second or something like that, pick and place. And on the line, you pick as many robots as you need to pick what is baked or made. And there are, in most cases, vision systems that guides the vision systems. They guide the robot to where to pick. Packaging. Handling and packaging together. This is picking heavy equipment like heavy parts like liquid, in this case champagne, and that is typically a very good example of where to use robots. Heavy objects in large volumes, and they are similar in shape. So what is difficult? Small series variants. That calls for reconfiguration, reprogramming, or managing a lot of things within the same systems. So we need a more flexible, adaptable system that gets more complex in a way. Collaboration. Collaboration means co-work or working together. Several robots or robots, humans in different kinds of setups. That creates complexity. Simple tasks made easy. In a way, I mean, that is easy to say, but it should be in a way that simple tasks should be made easy to operate by robots. But in most cases, it is that there is always a setup time for any task, even the simplest one. So it's extremely important to make simple tasks made easy in minutes. And complex tasks, of course. I mean, complex tasks tend to be very complex in time. But we come back to that one. Manufacturers, some example of manufacturers: Yaskawa, Fanuc, ABB Robotics, KUKA. Those four are the big four in the sense that they are the biggest in a way that produce any kind of robot, or most kinds of robots that are used for most applications in industry. And then we have players or manufacturers like Universal Robots. They are, or they, it is a very big manufacturer of robots of smaller sizes, up to 10, 20 kilogram payload, and very good at that, of course. Located in Denmark. Comau, Italian-based company, general purpose. Stoibli, adapt, and then further on. So there are numerous of manufacturers, 20, 30, or even more, for different kinds. And then there are some niche areas like clean room based robots for medical use and so forth. They're kind of special. Examples could be Mitsubishi, Epson, and so on. Some examples here: picking muffins. We use, or they use, vision systems to guide the robot, and as for the former example with the Delta type robots, have dedicated robots for that kind of picking. Then one might think that the faster is better, and that is true, but there is a limit how fast you can actually pick things like a muffin, because if you pick too fast, it will be destroyed. So one have to be delicate on these kind of objects, really, really delicate. And also the control of the motions has to be delicate, so they maintain the shape. Automatic wiring, that is special interesting case with also a kind of challenging object. One doesn't think about that wiring could be done by robots, but that can absolutely be done, and it's quite interesting that things like when we talk about quality could be enhanced, because what is programmed with the robot in this case, it will actually do. There are no mistakes done. But if a human is doing these kind of things, it's quite easy to understand that mistakes can be done, and there will be some errors if the wiring gets wrong in some places. So this is pretty interesting. So, developments and trends. Some trends relate to work process specialization. Dedicated robots for certain processes. Example could be spot welding or spray painting, for example. Tools, the same thing. Welding tools, spray painting tools, or whatever, or dedicated tools for polishing, grinding. Methods applied. Usually when we talk about certain processes, so those have to be programmed, and then there are some wizards or methods developed related to programming those methods, those processes in an efficient way. And then some general solutions and methods related to developing the technology as it is, related to increased use of sensors. That is a general way to see it. The collaborative robots is increasing, and as a matter of fact, within the ongoing work related to standards for robotic safety, the term collaborative robot will be taken away, but instead there will be collaborative applications, because a collaborative robot doesn't really exist by definition. It will be collaborative for a certain application if it is safe for that type of use. But that is not really dependent on the robot, but on the way the robot is used, the type of tools it is to be used, and so forth. So that is one thing one have to think about. And supporting tools, of course, programming, simulation-based programming, and so forth, and controlling processes and tasks. And the challenge related to this is a fast, cost-effective implementation, always when you change the way the robot system is used. And then one can also think about that the engineering costs are usually very high compared to the robot and other equipment. Typically, if a system is at 1 or 2 million Swedish crowns, then the cost of the robot is usually a quarter of that, or a third, something like that. The hardware. The rest is engineering cost, and whatever it is. Some examples of actually how can it look like from Automatica Fair in Munich. I took those myself just to see how things looks like. Well, this is a robot on server track, and at the same time also aligning its center point along other external things. Laser cutting. So the laser beams go through the robot arm, and there are different ways to do that, either by mirrors, if it is CO2 laser, or in a fiber-based laser system, if it is a YAG-based laser, because they have different wavelengths, so it depends how you really transfer the laser beam. Also, what type of laser you use is dependent on what material you want to process and for what purpose you are going to do. Grinding, in this case, there are knives to be grinded, and that is done in a quite nice way by a robot. And the robot takes the knives and moves it towards different types of sand, different tools to grind the knives to create a perfect edge. Then we have the Skara type of robot, which is a 4-axis assembly arm. It has a speed which is similar to the Delta arm, but a different configuration, and they are adapted for kind of different kind of applications. But they could produce more or less the same kind of things in most cases. But the Skara type of robot is a 4-axis. Apart from Delta, which is a 6-axis.
I should use it.
This is an example of a very fast motion by the Skara type. Welding, arc welding in this case, also some kind of specialized robot developed for that kind of purpose with hollow arm design, so that most of the cable for the arc welding process goes through the robot arm or very close to the robot arm. Okay, so development of an industrial robot. Well, the first patent of a robot was filed 1957, but about the same time or shortly after, there was a patent filed by George C. Devil, and from that, the first industrial robot was developed and deployed at General Motors facility around 1960-61. It was based on server drives, computers, memory developed just as after or during the Second World War. And 1951, the first numerical control machine was demonstrated at MIT, and the driving force behind numerical controlled machine tools was the aerospace industry to produce jet engines, for example. So they needed these kind of machines to do that. But robots, the driving force was actually automotive, car manufacturers, General Motors, Ford, and so on. Could look like this one. So the Unimate was a hydraulic powered robot that looks like the turret of a tank, more or less. So it was intended to take and manipulate hot metals from when you make motors for the car industry. So some characteristic features of those kind of robots from the beginning. In principle, there was an arm to move a workpiece in space, 3D, a wrist to rotate that workpiece around at least one axis, in most cases 2 axes or 3, a gripper to grasp or release a workpiece, enough load capacity. We talk about maybe 50 kilograms or something like that or more. Manual control and programming possibilities. Memory to record taught operations positions. Automated control of instructions. Movement speed not less than a human and reliable operation. And in principle, all of those could be accomplished at that time during the 60s, but also a low price. That is really a challenge to get that working. So the uptake of robots during the 1960s was really, really slow, but still, I mean, it was evident that this type of technology should come. It was something for the future. The typical usage during the early years was machine tending, materials handling, which is essentially more or less the same thing, but machine tending is actually machine handling for a machine. Machine handling is for anything like packaging or whatever it is. And then within automotive industry and electronics industry, which are the main industrial users. Some benefits and driving forces are easy change of operations, even quality, less scrap, better work environment, flexible with respect to your volume you are producing. Flexible in a way that if you think about, if you have humans, operators, working in the factory, so if you're not selling anything, you have to pay for their salaries, even if they're not producing anything, or you produce on stock and you hope to sell it later. With robots, you can just say that, okay, you shut down and okay, the investment is still there, you have to pay for that, but you don't pay anything else. You have no running costs if it's standing still, usually. And can cope with fairly complex operations. It really depends, because in some cases I would say that humans have the capability to do really complex things, but that has robots also, and they are usually complementary. So what the robot is good at, a human is bad at, and the vice versa. So, for example, a robot can easily pick up things like weighing 50 kilograms, hold it in a steady position within a tenth of a millimeter, whatever it takes, with no problems, and operate it in a very precise manner, which a human can never do. But the human is really good at picking a lot of small things with the hands and fingers, which a robot has some difficulty to do, really. But anyway, having said that, what we look at is where does the robot comes in. So if you have manual operation, it is usually at low yearly volume of a product. It's more or less the same cost per part, but not during the first production, so to say. But otherwise, it's fairly constant. If we produce a lot of products of the same type, so we have fixed, dedicated machines, which are more expensive than robots. But when we do millions of those products in very high volume, so to say, so the cost per part is very low. And in between, so there is where the robot comes in a more flexible manner. So robots are cheaper than dedicated machines, but they are usually slower. But they beat the manual worker in most cases, except for the very low yearly volume. And when we have reconfiguration for new variants of the product every day, so to say. So we have very low volumes. And this is expanding this area. And we can look at it at another way, where we have developments and complexity over time. So the value of the robot does not come from the robot itself, but how it is used and integrated within the manufacturer systems. And if we think about this with a flexible motion automation, where the robot replaces the worker, so that is fairly simple system. That was done during the 60s and 70s and 80s. And then we advance the systems and information integration in integrated manufacturing systems, and connect those many robots and other machines, quality assurance, quality control sensors, and so forth, with a high complexity. That was done during the 80s and 90s. And of course today also. And then we think about controlling processes at a higher level of abstraction layer models. We have difficult tasks. We move into one of production or very low volumes, which can be done if we have model-based control. And then we enter what we call Industrial 4.0 paradigm, the fourth industrial revolution, which we'll talk about later. And then the last, with the highest complexity, is really when we introduce decision making, planning, error recovery, and we have skill and intelligence within the system. In some sense, that is a part of research and development at the moment. In some rare cases, it has been implemented, but in general, we are at that place where artificial intelligence is coming within the next years, 5 years, 10 years from now, with a very high complexity of the systems, which it actually will change a lot of things.